thank you very much for the introduction and for the invitation. It's a great pleasure to talk here. Of course, it's very hard to talk after two excellent talks. So, well, before starting, so this is the content of my talk, and there is a zeros point in that, which is actually before the actual mathematical content of my lecture. It's about the breadth of Neumann's reputation. Recently, this spring, I was drinking beer with a Russian-American mathematician friend of mine, and he said that the greatest mathematician of the 20th century was definitely Neumann. I was modest. I told him, well, there were several excellent mathematicians in the 20th century, but he said, look at Wikipedia. So I looked at Wikipedia, and there is this part in Wikipedia someone is known for. And yellow means the subjects which Neumann is known for. So you can see the start of the list, and there is the continuation of the list, and at the end of this continuation, there is plus 93. Almost infinite. So, okay, I just looked up Einstein. Now there is Einstein in Wikipedia, so this blue, the achievements of Einstein, known for, so on this page and on the next page, not comparable. Of course, there is no sense to compare these giants of science, but that's an interesting remark. Okay, go to the actual content of my talk. Probably I will repeat some points, but that doesn't make any problem. So Neumann was born in 1903, so the father convinced him to study chemistry, so he studied chemistry in Berlin and ETH. During these studies, he made a PhD with Lipót Fejér, Hungarian excellent mathematician, about the axiomatization of set theory. We have heard about it today. Now, in 26, there was a big change in Neumann's life and his scientific interest. So from early autumn in 26, he went to Göttingen. And Göttingen was the center, a boiling center of science, of physics and mathematics. So you see who were there. So there was the birth of quantum theory. There were Heisenberg born. So you see the names. Actually, in italics, you see the names who later received the Nobel Prizes. 7 people received the Nobel Prizes, and probably Oppenheimer and Teller didn't receive the Nobel Prize because of political reasons, but that's not my topic to talk about it. So there was quantum physics in birth. Moreover, and I think this is why actually Neumann went to Göttingen, because Hilbert was there, and Hilbert had an interest in set theory, in logic. And Hilbert appreciated and influenced set theory, logic, and Hilbert was also interested in quantum theory, and in general, the neighborhood that year in Göttingen was 23. He was 23. So at this age, he could absorb a lot of new ideas, and he did absorb a lot of new ideas, and he was very much influenced. It's fantastic what he did. So you will see, actually, in the earlier talks, you could have already seen what he did, but I will now go to one problem which Hilbert was interested in. So mathematicians certainly know, but non-mathematicians might be interested to learn that. So Hilbert was a sort of leading personality in mathematics at this time. So in 1900. There was an International Congress of Mathematicians in Paris, and Hilbert, as a prestigious, most prestigious mathematician, he was asked to talk about some problems for the 20th century. So he collected 23 problems for the 20th century. And among these problems, there was one problem, the sixth problem, which the title is Mathematical Treatment of the Axioms of Physics. And this is the text from the beginning of Hilbert's formulation. The investigations on the foundations of geometry suggest the problem to treat in the same manner by means of axioms those physical sciences in which mathematics play an important part. In the first rank are the theory of probabilities and mechanics. As to the theory of probability, well, just one remark. So, foundations of geometry. We learned at school about Euclidean axioms from geometry. So that was the goal of mathematical theories, to repeat mathematical theories like geometry in Euclid's form. So, return to Hilbert's text. As to the axiom of the theory of probabilities, it seems to me desirable that their logical investigation should be accompanied by a rigorous and satisfactory development of the method of mean values in mathematical physics, and in particular in the kinetic theory of gases. So what happened before? What turned Hilbert's interest to this question? Actually, I call your attention that this formulation of the sixth problem is rather vague. And it's not surprising, because mathematics at this time was not sufficiently developed to give a more, mathematics of these subjects was not sufficiently developed to give a more precise formulation, but Hilbert definitely stressed the importance to understand this. So there were some results earlier. For instance, there were very nice, very beautiful results in a sort of naive probability theory. Fermat, Pascal, Bernoulli, Laplace, you see these names earlier, much earlier. I just remarked that the axiomatizations of probability theory only happened in 1933 by Kolmogorov. And the other topic is the birth of naive statistical physics. So in the 19th century, Gibbs, Maxwell, and Boltzmann, they were trying to give some more strict formulation of the theory of the kinetic theory of gases, for instance. In fact, Boltzmann had several papers about this, and he formulated an ergodic hypothesis, which was in terms of physics, so it was not well formed, it was roughly formed, but it certainly was important, and he formulated the ergodic hypothesis. Okay. Now, I will try to give some idea what had Boltzmann in mind. And I will try to give the simplest example for that. So understand notions like temperature, pressure of a gas. We completely understand. I mean, we think we completely understand what it is. So, but these guys, they wanted to give a better understanding. So, and processes like diffusion, heat transfer, and so on. So, let me focus on pressure. Well, there is, in this picture, you see, I'm not so, what did I do? Okay. No. Can you? Okay.
Do you want the video?
No, not yet. But I'm not so good as you were in this. So I would like to point to from.
Point on that. don't understand.
No. Oh. Okay. No. Okay, I will avoid it. So in this, this is a two-dimensional picture, and you can imagine it's particles of a gas. Each particle has they have equal masses, and each has a velocity. And you understand what pressure is. You understand that pressure is the following, that on the boundary of the square, how you measure, so you take some average in time in a unit surface, and unit time you take the average, and this is what we think it's a pressure. It's a very simple thing, but to give a precise mathematical explanation or physical explanation for that, it's not so easy, and this I will talk about. This is actually Boltzmann ergodic hypothesis that this pressure really exists, and what the goal is to derive the ergodic hypothesis, which I will tell you later what it is, from the atomic theory of matter, from Newton laws, from deterministic dynamics. Okay. So I will start with two very simple, the simplest mathematical examples before I go to more complicated models. So there is the head or tail. We heard about games. So head or tail is also a game. This is a sort of mathematical model of this game of head or tails. So this you should understand in the following way. On the left-hand side, you see a picture. It's a map of the interval. It's a map of the interval, and the formula for this map of the interval is on the upper right-hand side. It's called Tx. This is a map. And this is 2x if you are in the left, in the interval I0, and 2x minus 1 if in the right interval. Actually, mathematicians would say that it's 2x modulo 1. So this is the map of the interval. And if you take the second iterate of this map of the interval, then you can see on the right-hand picture how you get the iterates of a point x0. You get tx naught, which is x1, x2, tx1, and so on and so on. Now, a very simple fact that the length is invariant under T. What it means? That it means that if you take a small subinterval and you take the preimages, then it has two preimages and of half size, and the sum of the two halves is the same as 1. So it's this length is invariant. And one can introduce a sort of symbolic dynamics, which is following the trajectory of this point, and for every n, giving note whether it belongs to the left interval or the right interval, and this is epsilon 0 and so on, epsilon n. Now, it's very easy to see that this epsilon 0, epsilon n is a sequence of independent coin tosses, heads or tails. And we know that by the law of large numbers, if to add up all the epsilons until n minus 1 and divide by the number n, this converges to 1/2, of course. So if you take heads or tails for a long time, then approximately half of the tosses will be. And this is the law of large numbers. This is a very simple example. Now I will show you my last example, which is also a simple, a bit more complicated than the previous one. This is, Arnold's cat map. Well, this is a map of the square. So on the left-hand side, you have a picture of 2 times 3 squares. So I'm talking about the left lower square on the left-hand side. And you take an image by this matrix. It's easy to see that the image of this square will be this elongated parallelogram. And you can do the following. You shift each pieces in the other squares back to the original square. So it's easy to see that if you take the blue triangle, you can shift it back to the original square and you get a blue triangle. The same for the yellow one, the same for the green one. Altogether, you get the same square as you started with. This map is called Arnold's cat because Arnold, a Soviet-Russian mathematician, he wanted to illustrate this in a more interesting way. So he put a cat in this square. He considered the image of the cat first in the parallelogram. You see this elongated picture. And then shifting back the pieces to the original square, you get this rightest hand figure. And this is the image of the cat under one iteration of the map. And again, as I told you, the area is invariant under T. So I showed you these 2 examples because they are the simplest examples of a theorem, of ergodic theorem of Neumann. Now, what Adler and Weiss, also in 67, they found that they could decompose this original square into 3, on the picture they are rectangles, the green one, the red one, and the yellow one. Well, when I am talking about rectangles, there is one thing which I want to explain at this point, that these are, of course, rectangles, not as you see them, but if you do the following, you imagine the square in the following way. You glue the opposing sides of the square to each other. Then, of course, you have a square. You have a square. You first turn and glue opposite sides together. You get something like that. And then the whole thing you can turn over again, and you get a swimming ring, right? And this is, mathematicals call it shorter torus. It's a 2-dimensional torus. And this is the 2D. So instead of the square, you should imagine the geometry of this swimming ring. And on the swimming ring, these are rectangles. Okay. And you can again do the same, that you make the iterates of this map, of the Arnold's cat map, and at every step you make mark to which part of this decomposition the image belongs, and you get again a so-called symbolic dynamics, epsilon 0, epsilon n. Now, this is not independent random variables as it was the case in the head or tail, but this is a so-called stationary Markov chain. Markov chain is not independent things, but random variables, random objects with no memory. So the present only depends on the previous step, but not the earlier history. Okay, and then for this Markov chain, there is also a law of large numbers, and again, the average converges to some value which is the mean value, the expected value of this thing. Okay. Now I go to Neumann's problem, and so what I told you that Birkhoff made a formulation, Boltzmann made a formulation which had no sense, no mathematical, some intuitive physical sense, definitely it had. It was an ingenious hypothesis, but no mathematical sense behind it. Now, in the beginning of the 20th century, ergodic theory dealing with these kinds of problems developed, and very clever people were trying to understand the notion of ergodicity, George Birkhoff, Bernd Kuppen, and André Weil. On the other hand, also in the early 20th century, something different happened, which we have heard already about it. So Hilbert, Schmidt, and Frederick Ries introduced infinite dimensional spaces. So the space which we think of is the Euclidean space, two-dimensional plane or three-dimensional or space. And one can think of 100-dimensional Euclidean spaces, but as these mathematicians introduced, there is also possible to think in terms of infinite dimensional spaces, which are much similar and much different from finite dimensional Euclidean spaces. But these are the Hilbert spaces. And it turned out that Hilbert spaces meant just the perfect mathematical language for quantum physics. And this was what Neumann also understood it. We heard that he had a joint paper also with Hilbert about this. And in fact, in these years, 30, 31, 32, perhaps already 91, 29 starting, he wrote a great book about mathematical foundations of quantum mechanics. So he knew about Hilbert spaces. He understood, and he applied them. Okay, so what happened then? Then he could formulate his ergodic theorem in 32, and I will give the formulation for the simplest case. So you take again a map of the interval, which preserves the length, we call it Lebesgue measure, mathematicians we call it. And this theorem says the following. Well, there is a Hilbert space behind all these things. I think not only mathematicians, but of course physicists, engineers are familiar with Hilbert spaces because you work with spectral decomposition. So this is behind all these, there are Hilbert spaces. So you take the space of so-called square integrable functions, and the theorem says that this average, so-called time average of this function exists, and it's this f bar limit, which depends on the point in principle. And also Neumann could add that this limit function is the projection of the original function to the space of t-invariant functions. So those functions which do not change under this map t. For instance, the constant function, if you apply a map to a point, the function is constant, so the constant function is of course invariant. This is just one direction in this space. This is a projection, not in a Euclidean space, but it's an infinite dimensional space. So he could characterize the limit. And then there is a mathematical definition that this map, this transformation is called ergodic if this limit set is consists of the invariant functions contain only the constant functions. It's constant functions, constant times a constant is also a constant, so this is a one-dimensional line, actually. So this is the only invariant function, this one. So this is the definition of ergodicity. And very briefly, when I started, can you tell me?
20 minutes. 20 minutes. You have 20 minutes.
20 minutes. Thank you very much. I will try to control myself. So now I will give you a one-page proof of Neumann's theorem. So this wants to illustrate what I said in the title, a small step for a genius, because it's really, now we understand it's a simple fact. It's a simple proof. I can give it in roughly one page. So if you have a constant function, if you apply this time average of the constant function, in the limit you get a constant, so no question. Now if you take functions which are of this form, some function g minus its map, tg, then it's very easy to see that if you take this sum, then g minus tg, tg minus t squared, and so on, this sum contains only two terms. And if you divide by n, which tends to infinity, then the limit is 0. Now, these two kind of functions, the constant function and functions which are of this form, g minus tg, easy mathematics gives that these functions are dense in our favorite Hilbert space, so the theorem is true for every function. So it's simple, right? Now, of course, I leave out some mathematical details, but at this point I want to make a remark that Neumann's ergodic theorem, so this limit can be understood in different ways, and mathematicians are eager to understand all the possible ways of these limits. So Neumann's ergodic theorem was formulated in this Hilbert space, so the claim of the theorem should be understood in this space of square integrable functions. And Neumann's theorem doesn't say that the same limit exists for almost every initial point. Not for every, but for almost every. And this is an additional a different statement. And actually what happened in the history that Neumann already understood his theorem, and Neumann was a sort of, his life was mathematics in a leisurely way. So he lived in mathematics, he wanted to discuss mathematics with everyone, and so he also discussed mathematics with George Birkhoff, telling him his proof of the so-called mean ergodic theorem. This is the Neumann ergodic theorem. And of course, the problem arose whether this kind of for almost every point, is it true? This appeared. And Neumann was doing a lot of things parallelly, so he was certainly writing his book, he was working on game theory, and so on, logic. So he didn't focus so much on trying to prove this. And Birkhoff proved, and there is a history which is written actually in several places, that Birkhoff was the editor of the journal where Neumann wanted to publish his paper, and somehow Birkhoff arranged that his paper first appeared, though Neumann's results was the first. But later, this problem was arranged gentlemanlike, so from the side of Birkhoff too. So now we know what the history is, and of course, both are great mathematicians. Okay. Now, so the question arises, what about, so I told you that there is this Neumann's ergodic theorem, and we say that this map is ergodic if the limit function is constant. So now I would ask the first video, this one. So these are 5 disks in 2-dimensional. You should understand it's a gas. And there are 5 particles which collide according to Newton's mechanics. And this is on the torus. So here you see what we mathematicians call torus. So if there is a disk going out on one side, it returns on the other side, and the colors mean the energy of the particle. And so Boltzmann's original conjecture somehow was about the following. If you take a gas of particles, then you can measure pressure on the boundary. Well, the torus has no boundary. I will later go to the case when there is a boundary. But even in this case, you can check the energy which comes to a surface of unit measure on this square from one side. And this would be the pressure. So the question is whether this system is ergodic. And, okay, thank you. And Sinai in 1993 formulated the following hypothesis, that if you take any number of hard balls on any dimensional, or 2-dimensional, 3-dimensional, whatever, that this system is ergodic. So pressure exists. It does not happen. The following thing, of course, we know it does not happen, but mathematically we have to prove. It could also be that there is a limit, and with half probability, the limit is 2. With half probability, it's 1/2. And this could be, but it is not so, and this is what Sinai's hypothesis was for this model. So N is ergodic. Actually, Sinai in 1963 saw that he can prove it, but when he worked out the proof, it turned out that it was a great result, that he could prove that 2 disks on the 2-dimensional torus system of 2 elastic disks colliding, this is ergodic. And later in 1987, they could extend the results for arbitrary dimensions, but only 2 balls. And the method which Sinai worked out for this, for proving the ergodicity, he started the theory of so-called hyperbolic dynamical system with singularities. And this method became substantial in the theory of chaos. You know the butterfly effect, so behind the butterfly effect there is this kind of hyperbolic behavior. And I repeat here Arnold's cat, which shows that what is important, that you have this expansion, poor cat. So there is expansion in one side, and because of singularities, it's cut into pieces. So this is the simplest example of a hyperbolic dynamical system with singularities. Of course, there are much more interesting examples. For example, you can have heard about the Lorentz attractor. There is also the same phenomenon, that there is hyperbolicity, this expansion and contraction in the other side. So this is what hyperbolicity is about. I don't have time to talk more about it. Now, Sinai studied for his result in 1970, he introduced the Sinai billiard. It turns out that arbitrary number of balls, it's this kind of billiard. So the dark circles. These are on the torus. There are circles. These are fixed so-called scatterers. And the particle, it's a point particle which moves, hits the scatterer, and according to elastic reflection, it gets collided. So this is the Sinai billiard. And the important observation that arbitrary number of balls on the torus is isomorphic to a Sinai billiard. Now, here you saw, I mentioned the results of Sinai and Chernoff-Sinai, the two discs or two balls in arbitrary dimensional torus, it's an ergodic system. Now, I told about this isomorphy to a Sinai billiard, but the scatterers in the case of two balls are strictly convex, like on the left-hand side. So if you have this wave front, after one collision, it gets strictly convex after one collision. And if you have three or more balls, then it does not get strictly convex, but only scattering in one direction, in the other direction it's not. So that's an additional problem, and so Sinai and his school, they could not solve it, and this is what we could treat first, 3 and 4 balls, and then with Nándor-Simányi we could prove that almost the hypothesis of Sinai that n balls on the d-dimensional torus ergodic, typically only. So for almost, we were applying algebraic geometric method. We understood that it's not important, but Nándor-Simányi, for Nándor-Simányi it took 14 years to get the complete answer to the, okay, now what about general interactions? Not only these hard ball collisions of hard balls, which I mentioned. And I think perhaps my time does not permit to go much further, so I want to finish on this at least. So Kolmogorov, Arnold, and Moser, actually Kolmogorov found the idea and he gave a sort of the idea of the proof, but he didn't work out the complete proof in 54, that if you take other interaction than this hardcore collision of hard balls, of billiard balls, then the system is not ergodic. There are unpleasant initial configurations when you don't get this ergodicity, you don't get the pressure correctly. So after this negative result, now the expectation is that if you have a different interaction, then you have one large ergodic component, which is getting larger and larger as the number of the particles tends to infinity. Now, returning to Birkhoff. Birkhoff wanted to give the proof of ergodicity, and he worked a lot on it in general. We see that the system is not ergodic. So, in a sense, he worked in vain. And this is what, so there is a book by Hirsch about Peter Lex. And computers also serve as laboratories for mathematicians. New mathematical relations can be discovered, and our hypotheses and assumptions can be disproved or found more likely by computations. So this shows how Neumann's interests were coupled, computers and mathematics. Lux mentioned George David Birkhoff's lifetime effort to prove the ergodic hypothesis before computers were available. If Birkhoff had been able to test the hypothesis on a computer, he would have found examples where this is not true. By the way, This morning, when I was coming here, I was trying to look up. I know Peter Lex is a Hungarian-born Abel Prize winner mathematician. He left Hungary at the age of 15, and in 41, and he was very gifted. He also got to Los Alamos, where he met Neumann too, and there was an interview with Lux 10 years ago. And the question was that it's certainly true that for being such a tremendously influential figure in 20th century mathematics, von Neumann isn't remarkably well known today. Actually, I have met some Americans. One of them is a Oscar Prize winner film director, and also a regular contributor to National Geographic and other journals. And I asked him, and he hasn't heard about Neumann, so this is the case. And also other Americans did it. Why do you believe this is? Why did von Neumann fall to make as large an impact in the public eye as, say, Albert Einstein or Alan Turing? And Peter Lex answered, it's a mystery to me why von Neumann isn't a household name among educated people. The most powerful brain, father of the modern computer, uncle of the atomic bomb. This is the stuff of legends. And he was a legend in his lifetime among those who knew him. Perhaps an article in the New York Times on some anniversary could start the ball rolling. Well, I think my time is over. I would have talked much more about the influence of the ergodic theorem on science, so on the proof of atomic theory and also relation to Einstein, but I thank you for attention. Definitely I want to
Thank you very much for the presentation.
thank you very much.
Yes, this picture